So in this video, we're going to do a problem using Taylor polynomials. So we said that in the previous video that you have this sort of function and you can kind of approximate it with a nth degree polynomial. And this is this entire formula for the polynomial. You can write it a little bit as a shorthand notation as from k goes from 0 to n of f to the k of 0 all over k factorial x to the power of k. So if you want to write it a little bit nicer, that this thing just means all of this guy. Okay, so this is what we call Taylor series. Okay, and we can go to infinity and we'll talk about that a little later. Okay, so first we want to find the third degree Taylor polynomial at x equals 0 for f of x equals e to the x. So the first thing that you kind of want to do is you want a third degree Taylor polynomial. So if you look at the expansion, here is the third degree. Okay, so that means I'm going to stop right there. And I'm going to go all the way to the third derivative. Okay, so before I do anything, I have to take 3 derivatives. So I'm going to start off first with f of x, and we know that f of x is e to the x. I'm going to take a derivative of this. I'm still going to get e to the x. Take the second derivative. I still get e to the x. And then take the third derivative. And I'm still going to get e to the x. So nothing really changed. Now what we're going to do is plug in 0, f of 0. I'm going to get e to the 0, which is still 1. F prime of 0, I'm still going to get 1. F double prime of 0, I get 1, and f triple prime of 0, I still get 1. Okay, and now all I got to do is find my third degree Taylor polynomial. And if I write down the formula, it'll just be f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x to the third power. Okay, so all I'm just doing is I'm taking all of these, the formula that I just had, and I'm just plugging it in to the third polynomial. Okay, all right, so now all I got to do is just plug everything in there. F of 0 is just equal to 1. This is just 1 times x, and you have 1 over 2 factorial x squared. And then you have 1 over 3 factorial x cubed. Okay, you can just leave it like this. You don't necessarily have to expand it, but if you do want to, it'll just be 1 plus x squared over 2 plus x cubed over 6. Okay, so this is going to be the third degree polynomial that best approximates e to the x. Okay, so one thing that you can try to do is that you can actually try to estimate stuff. So for example, if you wanted to estimate e to the third power or e to the third power, all you have to do to estimate it is just basically plug in 3 into this polynomial. 1 plus 3 squared over 2 plus 3 cubed over 6. Okay, and then you can just put this in your calculator and you just get your answer. Now the question here is, why can't I just plug in e to the cubed? And the reason why is because actually your calculator does this in this way. Okay, so many calculators and many computer softwares cannot quite do something like this, and then when we get to integration, you'll see that you can't do something like that or integrate something that's not integrable. So one way that we can do it is make it a little simpler by making something that looks really complicated into a polynomial. Okay, so that's basically the gist a little bit about Taylor polynomials. So let's do another problem. Okay, so let's say we want to find the fifth Taylor polynomial at x equals 0 for f of x equals sine of x. Okay, so what we want to do first is remember that since we want the fifth degree polynomial, that's going to require 5 derivatives. So first we're going to start off with f of x equals sine of x. So let's take the derivative of sine of x. That's going to give me cosine of x. Then take the second derivative. That's going to give me negative sine of x. Take the third derivative. Okay, that's going to give me negative cosine of x. Take the fourth derivative. That's going to give me sine of x, and then take the fifth derivative. That's going to give me, what is this, cosine of x. Okay, and now what we're going to do is use your calculator and plug this in radians. Okay, so you're going to get 0 for this one. You're going to get 1 for this one. You're going to get, no, there's going to be 0. Take the third derivative. I'm going to get -1. Take the fourth derivative, plug in 0, I'm going to get 0. And take the fifth derivative, plug in 0, I'm going to get 1. Okay, so now all I have to do is plug in all of this information into my formula. So since I want a fifth degree Taylor polynomial, this is going to be f of 0 plus f prime of 1. Oh, that's wrong. F prime of 0 times x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed plus f to the fourth derivative at 0 over 4 factorial x to the fourth plus fifth derivative at 0 over 5 factorial x to the fifth. Okay, so now all we got to do is plug in all of my information. This guy was just equal to 0. This guy is just equal to 1, and then you have an x. This guy right here is just equal to 0, so the whole thing is going to be 0. Good. Then this guy right here is going to be equal to -1 over 3 factorial x cubed. Okay, so that one didn't go away. F prime of 4 is just going to be 0, so that's just a big fat 0. And then you have f to the fifth power. Fifth derivative, that's just going to be 1. So 1 over 5 factorial x to the fifth. So then when I plug this in, I'm going to get x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth. So here is going to be my fifth degree polynomial, because it's to the fifth power. So if we want to estimate, so let's say we want to estimate sine of 1.1, then instead of just using trigonometry, we can just use this Taylor polynomial to kind of tell us what it is, because this is a much easier function to plug into my calculator than the sine of it is. So just plugging in a number, I can try to estimate this guy, and basically what I'm going to get is 0.89159. Okay. Okay. So Taylor polynomials, as you can see in the previous problems that we've done, Taylor polynomials have been centered at 0, but they don't necessarily have to be centered at 0. So Taylor polynomials don't have to be centered at 0. Okay, they can be centered at any other value. So let's say I wanted to center it at some value a, then the nth degree polynomial centered at a would be f of a. So any number that I want to plug in, f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a squared plus all the way until I get to the nth derivative over n factorial x minus a to the nth. So notice that the only thing that changed in this case was that you are now plugging in a instead of 0, and then instead of the x you have a minus a. Okay, but nothing else has really changed. Okay, so we'll do one more problem. So let's say we want to find a second degree Taylor polynomial for f of x equals square root of x at x equals 4. So notice that it's not centered at 0 anymore. Okay, so because we want 4, we want to have 4 derivatives. Oh, no, I'm sorry. Because we want the second degree Taylor polynomial, we want 2 derivatives. Okay, so we're going to start off with f of x. I can write f of x as x to the 1/2. Then f prime of x is going to be equal to 1/2 x to the negative 1/2, and f double prime is going to be equal to negative 1/4 x to the negative 3/2. And now what we're going to do, we're not going to plug in 0 anymore. We're going to plug in 4 because that's where we want to center it at. It's going to be 4 to the 1/2. It's going to give me 2. Then we're going to plug it into the prime. So that's going to be 1/2. 4 to the negative 1/2. That gives me 1/4. And then the second derivative, plug in 4. I'm going to get negative 1/4. 4 to the negative 3/2. Put that in my calculator, and I get negative 1/32. Okay, so now what I'm going to do is plug in my second degree Taylor polynomial centered at 4. That's just going to be f of 4 plus f prime of 4 x minus a, which in this case is going to be 4, plus f double prime of 4 over 2 factorial x minus 4 squared. So all we have to do is just plug everything in there. So this guy is just this guy, which is 2. This guy right here is just 1/4 x minus 4. And then this guy right here is just going to be this negative 1/32 over 2 factorial x minus 4 squared. Okay, so you can kind of leave it like this if you want to. Okay, so that's essentially what these Taylor polynomials are doing. Okay, so graphically, this is what's going on. So I'm not going to do any more math in this video, but what I kind of want to show you is basically what is the whole point of this. Like, why are we taking the sine function? If we already know what sine is, you know, why are we doing this whole thing? What is the meaning of this polynomial? So what I'm going to show you in Desmos is the following. So here, have the function at f of x equals sine of x. So you can see the red function is just a sine function, it's just a sine wave. And then you see the purple function is going to be the Taylor polynomial. So here I'm going to center it at 0. Okay, you see a equals 0. And here we're going to do a first degree Taylor polynomial. And you'll see what's going to happen when I try to do it. So first we start off with the n equals 1. So you can kind of see that it's really, really close. But as n starts to increase, this is a third degree polynomial, and then a fifth degree polynomial, you start seeing that the graph starts to trace a sine function, which is actually pretty cool. So you have this polynomial function that as n gets larger and larger and larger, you start to trace out the entire graph. So as n gets larger, the graph starts to trace the sine function much more nicer. And that's what basically Taylor polynomials are doing. As n gets larger, you get to trace more of this function. And it's easier for us to deal with polynomials n to some power than it is to deal with sine and cosines and natural logs and exponentials. So that's basically the basis of Taylor polynomials.